Section: Introduction. In this section, we address the challenge of performance prediction in various industrial systems, including aspects like latency, execution times, and scheduling conflicts. Traditionally, we relied on expert knowledge to model specific metrics. However, recent approaches have shifted towards data-centric methods using machine learning regression, where we train models to predict a metric based on a set of features. Standard regression techniques, like random forests and multi-layer perceptrons, require features to be presented as flat, fixed-length arrays, which can be problematic for complex prediction tasks. Even if we manage feature engineering, reducing features to mere numbers can lead to significant loss of context, negatively impacting predictive accuracy. Gray box methods have tried to combine domain expertise with machine learning, such as learning coefficients for established symbolic expressions, but these often need extensive prior knowledge and can be quite restrictive. The emergence of language models has introduced text-to-text regression, helping us avoid many issues related to traditional feature engineering. Recent findings show that even smaller models, which we call regression language models, RLMs, can achieve impressive transfer learning when trained on large datasets of input-output pairs. These models can enhance prediction accuracy by learning from various regression tasks. Interestingly, training these models using next token prediction on numeric data is efficient and can match or exceed the performance of standard regression methods. In our work, we demonstrate that RLMs can effectively simulate efficiency outcomes by training on extensive data from large-scale systems like Google's Borg compute cluster, leading to significant cost reductions. Our contributions include showing that RLMs can predict numeric outcomes, such as efficiency metrics for industrial systems, with high accuracy across complex feature representations. By fine-tuning with minimal new training data, these models can adapt quickly to new scenarios. We also provide detailed analyses of how factors like sequence length, model size, feature observability, architecture, learning rate, and early stopping influence performance, along with the model's ability to quantify uncertainty. Next, we give a brief overview of Borg, Google's compute management system. It consists of a central manager that schedules jobs across various machines with computing resources. Users submit task requests that include executable files and details about resource needs. The manager's job is to allocate tasks to suitable machines based on resource availability. To allocate tasks effectively, the scheduler must understand the resource consumption and productivity of each task, which is measured as millions of instructions per second per Google Computing Unit, or MIPS per GCU. This metric indicates how much work is accomplished per unit of time for each computing resource used. We can calculate MIPS per GCU by profiling the total instructions executed and CPU cycles used over a 10-second period. Many factors can influence this metric, including current memory and CPU usage, hardware types, and workload distributions across machines. Time variations can also play a role, as workloads depend on user patterns in specific geographic areas. Additionally, hyperparameters that affect the bin packing algorithm can significantly impact outcomes. Fortunately, Google has created a digital twin of Borg, a sophisticated framework that uses real-world cluster data to simulate scheduling and calculate overall MIPS per GCU. However, generating a single outcome can take between 1 to 18 hours of computation. These outcomes are valuable for training regression models, even though the data is limited. If we can accurately predict this metric with minimal inference time, we can save on computation costs and optimize MIPS per GCU more quickly. For example, Google Vizier is used to tune the Borg scheduler's hyperparameters, but its Gaussian process regressor is limited to tabular data formats, which restricts its predictive and optimization capabilities. Section Summary. In this section, we discuss the challenges of performance prediction in industrial systems, highlighting the limitations of traditional machine learning methods and the advantages of regression language models, RLMs, in predicting complex metrics like efficiency in Google's Borg compute cluster. We emphasize RLM's ability to adapt quickly to new data and improve prediction accuracy while reducing computational costs, thus enhancing overall system optimization. Section: Prediction Task. In this section, we focus on the prediction task, which aims to forecast the efficiency metric of MIPS per GCU. This involves predicting a single floating point number after applying a specialized bin packing algorithm, based on the initial state of the compute cluster, the time frame for data collection, and the hyperparameters of the scheduling algorithm. We can use various pieces of information as input features, including the cluster name, its physical location, the time window for data collection, hyperparameters influencing the Borg scheduler's bin packing algorithm, and details about concurrent teams using the compute resources. We also consider the distribution and network structure of the hardware in the cluster, along with job performance profiling results. While we believe these features are significant, it's not always clear how they impact the efficiency metric. For instance, the efficiency metric is closely tied to the specific cluster, but the cluster name itself isn't a direct feature. Timing windows and hyperparameter names can overlap across different tasks, yet they may influence efficiency metrics in unique ways. Additionally, the prediction task can evolve as new feature values emerge from hardware upgrades or changes. The features can vary in type, including categorical hyperparameters and cyclical timestamps, and many features are deeply nested, such as job profiling data that includes job and machine information. We also recognize that the metric can be affected by various forms of noise, some of which depend on the features observed. To define our prediction task broadly, we assume there is an underlying distribution that describes the relationship between the observed features and the target metric. The randomness from this distribution introduces irreducible noise, known as aleatoric uncertainty, which limits the performance of our regression model. For Borg, this randomness can stem from the bin packing algorithm and fluctuating load demands. If our model can only observe a limited subset of the full state, it may struggle to differentiate between similar inputs, leading to epistemic uncertainty and further increasing the variance in our predictions. To estimate the total variance and provide lower bounds on the mean squared error of our regression methods, we can analyze an offline test dataset. We also discuss the challenges of using traditional tabular regression methods, which can struggle to represent the diverse features we have. Many features, like job lists, can vary widely, requiring complex grouping methods. If new classes of machines or workloads arise, we would need to start the process over, invalidating previous training data. In contrast, a flexible text-based input representation allows us to handle variable-length inputs without needing to explicitly define all categorical features or normalize continuous ones. By capturing all available features, especially those that are complex and nested, we can reduce epistemic uncertainty and enhance our model's performance. Moreover, this text-based approach enables us to adapt quickly to new data without starting from scratch, allowing for efficient fine-tuning and knowledge transfer from previous training. Section Summary. In this section, we outline our prediction task to estimate the MIPS per GCU efficiency metric using various input features related to the compute cluster's state and scheduling algorithm. We emphasize the challenges of representing these features in traditional tabular formats and advocate for a flexible text-based regression approach that minimizes epistemic uncertainty and adapts easily to new data. Section: Method. In this section, we outline the technical details of our regression language model, RLM, which is mainly based on OmniPred. For a comprehensive overview of standard language model training and fine-tuning, we direct readers to relevant surveys. We begin with the basics of text-to-text regression. In a typical language model setup, we update the model by minimizing the loss associated with predicting the next token in a batch of prompt-response pairs. In our case, the prompt represents a string for a variable x, while the response is a textual representation of a floating value y. This training can utilize any dataset since string representations are universal. During inference, we interpret the model as a density estimator, allowing us to make predictions by aggregating samples drawn from the model. Next, we discuss our design choices, some of which may go against common beliefs. We train using cross-entropy loss over tokens instead of error-based loss, like mean squared error, for an additional value head. This approach leads to more stable training across various y values and avoids overemphasizing tasks with larger prediction errors. We have observed that methods relying on embeddings or logits often perform worse than directly decoding numeric predictions. We also note that many current large language models, LLMs, use only a decoder architecture, which simplifies design by merging prompt-response pairs. However, our findings indicate that separate encoder layers are essential for handling complex inputs, making decoder-only layers less effective. Regarding pre-training, we argue that using a pre-trained LLM checkpoint is not always necessary or beneficial for training a regression model. Research has shown that we can effectively perform tabular regression with a randomly initialized language model, as regression primarily involves learning correlations between structured tokens rather than relying on the semantic meanings of words. When it comes to tokenization for y values, we emphasize that cross-entropy loss does not account for numeric distance, as tokenization discretizes the real number line. To optimize this, we minimize the vocabulary size for representing floats. We adopt a specific tokenization method where a floating value is represented using special tokens for the sign, mantissa, and exponent, allowing for normalization-free training across multiple tasks. Our model operates as a context-free regressor, processing a single x to return a single y, rather than handling multiple x, y pairs in context. This maximizes the sequence length for a single x, enabling the model to absorb unlimited data without being constrained by context limits during inference. This approach is similar to using random forests and multilayer perceptrons instead of Gaussian processes in traditional regression. Finally, we allow for fine-tuning our RLM with additional data after pre-training. This serves two purposes: adapting to new regression tasks and refining performance on previously encountered tasks. We can restore the weights and optimizer state from a pre-trained checkpoint and continue training with a lower learning rate on new data. The number of new examples can be quite small, effectively replacing in-context learning with gradient updates. Given our model's relatively small size, this process is quick, taking only a few minutes on a single GPU. This can be viewed as a form of meta-learning, where pre-training enables rapid adaptation to new tasks. Additionally, since the model can recognize task identifiers, it can perform regression across multiple tasks by pre-training on all task data and then fine-tuning for new tasks. Section Summary. In this section, we outline the technical details of our regression language model, RLM, which utilizes a text-to-text regression approach to predict floating values from string representations. We emphasize design choices such as using cross-entropy loss for stability, incorporating encoder layers for complex inputs, and employing a context-free regressor that maximizes sequence length efficiency, while also allowing for fine-tuning on new regression tasks with minimal data. Section: Regression Scaling Paradigm. In this section, we discuss the regression scaling paradigm. We maximize scaling across multiple dimensions using the RLM. We identify that the two key factors for effective regression are having diverse training data and ensuring feature observability. Since regression relies on understanding how functions behave continuously, meaning that if two inputs are close, their outputs should also be close, better observability helps our model learn these relationships more effectively. Additionally, having more training data allows us to cover a wider range of input scenarios. We note that other factors, like model size, are less critical because regression tasks do not require large models for generating text. We can also reduce sequence length requirements if users with domain knowledge can simplify string representations by removing unnecessary characters and prioritizing important features at the start. For our study, we use a model with a two-layer encoder-decoder structure, containing 60 million parameters and a maximum sequence length of 2000, which yields satisfactory results. In our experiments, we focus on performance prediction for Google's Borg compute cluster, but our findings are applicable to any large system using text-to-text regression. We conclude that maximizing feature observability significantly enhances regression performance, exceeding previous benchmarks. Large-scale pre-training on extensive datasets is essential for effective transfer learning and adapting to new tasks. RLMs demonstrate versatility, allowing for both point-wise predictions and density estimations while efficiently scaling with data, model size, and sequence length. For our specific application, we define a task as a set of 28,000 to 56,000 state outcome pairs collected from a cell over a month. We randomly shuffle these pairs into training, validation, and test sets in the 10th of October 80 ratio. The model can be pre-trained on multiple tasks and evaluated either within the same distribution or on new, unseen distributions. To ensure high-quality benchmarking, we use a pool of 40 cells with the largest variations in outcomes. We assess regression performance using various metrics, including mean squared error and scale invariant Spearman rank correlation, to avoid biases from different outcome scales. We begin our results with a case study on the RLM's ability to perform regression with sufficient training data. We pre-train the RLM across 8 tasks, totaling about 1 million data points, and achieve a rank correlation of 0.86 when evaluating within the same distribution. When fine-tuning on a new task with only 512 examples, we still achieve strong results, unlike a randomly initialized model, highlighting the importance of pre-training. We also present a kernel density estimate plot showing how well the model captures target points over time. We observe that the RLM's output can express multiple modes, reflecting its ability to learn complex relationships. We compare the RLM's performance against theoretical baselines and find that it produces significantly lower residuals, emphasizing the value of maximizing feature observability. Our results further illustrate the benefits of large-scale pre-training, especially for transfer learning. While in-distribution performance shows minimal gains with more tasks, out-of-distribution results improve significantly with increased task variety. We confirm a strong correlation between the variance of our model's predictions and the residual errors, indicating that our model appropriately reflects uncertainty. Finally, we present a comprehensive set of benchmarking results, demonstrating the RLM's capability to perform inference across various tasks. We achieve precise point-wise regression in low-noise tasks with high Spearman rank correlations. In tasks with higher noise, the RLM effectively performs density estimations, capturing diverse modes. We quantify the RLM's gains through explained variance and pseudo-R-squared metrics, showing its strong predictive capabilities across different tasks. Section Summary. In this section, we highlight that maximizing feature observability and utilizing diverse training data are crucial for improving regression performance, while model size and sequence length are less significant. Our experiments demonstrate that large-scale pre-training enhances transfer learning capabilities, allowing our regression model to effectively predict outcomes across various tasks, achieving high accuracy and density estimation even in the presence of noise. Section: Cross-entropy loss. In this section, we explore the connection between cross-entropy loss and traditional regression metrics like mean squared error, MSE, and Spearman rank correlation. During our training runs, we assess all saved checkpoints and categorize them as underfitted or overfitted based on the validation loss curve. We observe a direct correlation with MSE, and interestingly, we find that overfitted models can still achieve higher rank correlation. We also highlight the significance of processing the input with encoders. When we compare models of equal size, we discover that encoder-decoder architectures outperform decoder-only models, even with bidirectional attention. This contrasts with designs like Gemma and Llama, which are solely decoder-based. We suspect that while decoder-only models excel at generating outputs from simple prompts, they struggle with more complex inputs, though further research is needed. Our findings indicate that larger models with more parameters improve regression performance, but this improvement plateaus around 100 million parameters, which is much lower than the 1 billion parameters seen in state-of-the-art models. This suggests that our text-to-text method is broadly useful and requires relatively low computational resources, such as a single GPU. We also note that increasing the input length allows the model to capture more features for predicting outcomes, leading to lower validation loss. However, once the input length exceeds 3,000 tokens, the additional tokens mainly represent less important features, which explains the diminishing returns. Our model's behavior aligns with our domain knowledge. For instance, the performance of a cluster is influenced by temporal cycles, such as fewer jobs at night or weekends. The model's performance improves significantly when it includes time window features in its input representation. Lastly, we provide insights for future practitioners on optimal fine-tuning settings. We find that selecting the right learning rate is crucial for minimizing prediction errors when fine-tuning on multiple examples. Additionally, using earlier checkpoints from pre-training can yield better results for out-of-distribution tasks, as overly pre-trained models may struggle to adapt to new tasks that differ significantly from their training.